Hello everyone, welcome to DataByteSun YouTube channel. Today we are diving into a core concept in predictive modeling, simple linear regression. It is widely used, super practical and perfect for making sense of relationships in data. So what's the big deal about linear regression? Let's dive in and find out. Imagine drawing a line through data points to predict future trends. Let us say we want to predict a company's profit based on its advertising costs. By definition, linear regression is a statistical method used to model the relationship between a dependent variable y and one or more independent variables x. In simple terms, it's like finding the best fit line that closely matches the data points. So here our goal is to find the linear relationship between variables, often for prediction or understanding data trends. Let us talk about the applications of linear regression. Here are some real-world scenarios where linear regression is very useful. First, we can predict house prices based on size of house. Here we can try to capture how features like square footage influence the price. Another common use is estimating a company's profit based on advertising spend. More advertising generally leads to higher profits, and linear regression helps us model that relationship. Lastly, linear regression is used for forecasting temperature changes over time. By tracking temperature trends over time, we can make future predictions based on past patterns. Linear regression really shines in scenarios like this, where understanding relationships is key. Before we start predicting, let us go over the main assumptions of linear regression. First, linearity. X and Y should have a linear relationship. Next, independence, meaning each data point should be unaffected by others. Then there is homoscedasticity, which just means the spread of errors is consistent. And finally, we assume errors are normally distributed. Let us take a closer look at each assumption. The first assumption is linearity, which means that our independent and dependent variables should form a linear pattern. If you are seeing a nice straight line trend between x and y, we are on track. But if the data forms a curve or a non-linear pattern, linear regression won't work well, and we would need more advanced techniques to capture that non-linear relationship. Now let us look at the second assumption. Error terms should be normally distributed with a mean of 0. Each x has a set of small random differences or errors between the actual and predicted values. In linear regression, we assume these errors follow a bell curve shape centered at 0, meaning no consistent bias towards overestimating or underestimating like in this first histogram, where error terms are normally distributed. If our errors follow the pattern, like in the second histogram, our predictions might be biased or inconsistent, where error terms are not normally distributed. You will get better understanding of it while we do a practical over it. Next, we have the independence of errors. Here each error term should be independent of the others. In the first plot, there is no pattern, which is what we want, where no visible pattern and error terms are independent of each other. But if there is a visible pattern, like in the second plot, it means our errors are dependent on each other, which can disrupt accurate predictions. Finally, assumption number 4, homoscedasticity. This means our errors should have a constant spread or variance. If the spread of errors changes, like in the second plot, it's called heteroscedasticity. Ideally, we want a consistent spread like in the first plot to ensure a repeatable model. Now let's break down the main ideas in linear regression with an example. Imagine a company wants to know how much to spend on advertising to maximize profit. Advertising cost is our independent variable, x, which used to make predictions about y, and profit is our dependent variable, y, which we want to predict or understand. When we plot advertising costs and profits, we often see a straight line relationship, which is where our linear regression model comes in. This yellow line represents our best fit model. Remember, here is our key assumption is there is linear relationship between x and y. Let us break down this orange line into three simple parts. First up, we have the intercept. This point called beta naught is where the line crosses the y-axis. It shows us the value of y when x is 0. Think of it as a starting point of our line on the graph. Now let us look at the slope or beta 1. The slope tells us how steep the line is. It shows us how much y our prediction changes for each step we move in x. If beta is positive, our line slopes upward, meaning y goes up as x goes up. If beta 1 is negative, the line slopes downward, meaning y decreases as x increases. And then we have the error term, which is the difference between actual and predicted y values. Let us say we have a point xi. For that xi value, we have both a predicted y value on the line and an actual y value from our data. The distance between the two, marked in red here, is the error. We want these distances to be short, meaning our predictions are close to the actual data. Now putting it all together, we have our linear regression equation, y equal to beta naught plus beta 1x plus epsilon. This equation sums up our line. Here, y is the predicted value, beta naught is the intercept, b1 is the slope, and epsilon is the error. This equation helps us use the line to make predictions about y based on different values of x. Alright, let's take a closer look at how we calculate the slope and intercept for our line. The slope, which we call beta 1, tells us how much y changes for each unit increase in x. Basically how steep the line is. To calculate the slope, we use this formula. Beta 1 equal to summation of xi minus x bar into yi minus y bar divided by summation of xi minus x bar whole square. Here is what each part means. Xi and yi are each data point for x and y. X bar and y bar are the averages of x and y, sometimes called the means. This formula calculates how much y changes on average with each increase in x. The intercept, which we call beta 1, is where the line crosses the y-axis. This is the starting value of y when x is 0. We calculate the intercept using this formula, beta naught equal to y bar minus beta 1 x bar. Let us tackle a practical problem to see this in action. We will look at the relationship between our studied and test scores using data from 5 students. Our task is to fit a linear model, find the intercept and slope, interpret coefficients, and then predict a score for a student who studied 3.5 hours. Take a moment and think about how you would approach this. First, we calculate the mean of x and y using mean formula, which is calculated by adding all the values of a variable together and then dividing by the total number of values which we will need for finding the slope. Now plugging in our values into slope formula, we find that the slope is 7. Now using that slope, we find the intercept, which is 49. Our linear equation of final model is y equal to 49 plus 7x. This means 49 is the best score if 0 hours are studied and each additional hour adds 7 points. If we want to predict the score for 3.5 hours of study, we plug it into our equation y equal to 49 plus 7 multiplied by 3.5. Thus, a student who studies for 3.5 hours is predicted to score approximately 73.5 on the test. The plot shows the line which satisfies our equation over a test score and hours studied. Now, why is this line the best fit? There are many lines possible we can draw, so how to find which one is the best among all possible lines? To find the best fit line, we need to minimize the difference between predicted and actual values. And our goal is to minimize the sum of squared differences between actual and predicted y values. Y square we will get to know from further slides. So, we need to minimize the distance of these points which are currently showing so that every point have the lowest possible distance. That is where residual comes into the picture. A residual is the difference between an observed value and the value predicted by a model. The formula for residual for each point is residual equal to y actual minus y predicted. To measure how well our line fits, we calculate the residual sum of squares, which is in short RSS, and formula is given by RSS is equal to summation of y actual minus y predicted whole square, where y actual is the actual value, y predicted is equal to beta naught plus beta 1x is the actual value predicted by the linear model, with beta 1 as the slope and beta naught as the intercept. RSS or residual sum of squares measures the total difference between observed values and predicted values in a regression model. It is squared to ensure all differences are positive, emphasizing larger errors and allowing for easier mathematical manipulation. Lower RSS means a better fit. Now we have R squared, a metric to assess how well the model fits the data, representing the proportion of variance in y explained by x. R squared values are always in range from 0 to 1. The closer R squared is to 1, the better the fit. In plot 1, we observe a high R squared value, indicating a strong fit of the model, as it explains a significant proportion of the variance in the dependent variable. In contrast, the other plot, with an R squared value of 0.24, suggests a weak fit, revealing that only 24% of the variance is accounted for by the model. Such a low value generally indicates that the model may not be suitable for linear regression and may lead to unreliable predictions. Remember, an R squared value closer to 1 suggests a better fit. Finally, let's discuss limitations. Linear regression only works with linear data. For non-linear relationships, it doesn't capture the curve accurately. Plus, outliers can skew our line. So to wrap up, we have covered the basics of linear regression, assumptions and examples of linear regression, the equation, fitting the line, and its limitations. Thanks for joining me today. Be sure to subscribe to DataByteSun Consultancy for more insights. See you next time.